Hello and welcome back to another lecture of this week, like week 8 of NPTEL course on thermal physics. Now, in the last class, we talked about Carnot engine. We talked about we solved several problems on Carnot engine, and there are two more problems that we wanted to do in the last class, but could not finish. So, let us quickly start with those and then we will continue. So, let us start with problem number 5 and 6 for today's lecture. And first problem is that Carnot engine, whose low temperature reservoir is at 70 degree centigrades, has an efficiency of 40%. Yeah. So, it is desired to increase the efficiency to 50%. By how much? So, now we have to increase it from 40% to 50%. By how many degrees should the temperature of the source be increased? Okay. So, let us first examine this, let us go back quickly to this last week's note to begin with. Right. So, we see this efficiency expression for Carnot cycle or Carnot engine is eta is equal to 1 minus T2 by T1. Now, as we have seen in the last problem that the limiting case when T2 goes to 0, we have eta is equal to 1, but once again that is an idealized situation because T2 can never be equal to 0, as it is also it is by the third law of thermodynamics. We will come back to that towards the end of this course, but in general if I decrease T2 the efficiency will increase, or if I increase T1 the efficiency will also increase, right. So, there are two ways of doing it. In order to increase the efficiency of a given Carnot engine, which is where the engine is fixed, we have to change the temperature of the source or the sink, whether we have to increase the temperature of the source or we have to reduce the temperature of the sink. So, there is another limit when T1 goes to infinity, the efficiency also goes to 1, which is the maximum possible value for an engine. So, either we have to have a very high like infinite temperature, or we have to have a 0 temperature of the sink. Infinite temperature of the source or 0 temperature of the sink. Both of these are not possible theoretically. Okay. So, let us go back to this today's notes. So, we have this is the given data, n is equal to 0.4 and T2 is equal to 70 degree centigrades, which is 343 Kelvin. So, from there we can immediately compute the value of T1. T1 will be equal to T2 divided by 1 minus eta, which is 3. So, please remember this is 40%. 40% means in scale of 0 to 1 it is 0.4. 50% means in the scale of 0 to 1 it is 0.5. Right. So, either we can represent it as a fraction, or we multiply it with 100 and represent it as percentage. Right. So, T1 will be equal to T2 1 minus eta. So, which is 343 divided by 0.6, 571.66 Kelvin. Now, we need so that is the temperature of initial temperature of the source. Now, when we have eta prime is equal to 0.5 for sorry, just a minute, I think I just made a mistake here. By how many degrees should the temperature of the source be increased? Yeah, so that's a mistake actually. That's a mistake. What I did here is actually by how many degrees the temperature of the sink be decreased, but that is okay. I mean, you can do it for okay. What I did is not exactly what is asked in the problem. So, that is a mistake from my end. So, what I did is I calculated the new temperature of the sink, which is 283.83 Kelvin, which is 10.83 degree centigrades, which gives an efficiency of 0.5, right. So, the difference between the sink temperature has to be decreased by, right, no, this should be not 57.16, it is a mistake actually, just a minute. but I think you got the idea. So, what can be done? So, it is 343 minus 283.83. So, it is 59.17, sorry, not 47. So, 59.17, right. Kelvin. Right. So, this is the right answer, but once again what I did is I have calculated the temperature of the source that has to be decreased, but if I want to increase the temperature of the temperature of the sink, that is decreased by almost 60 degrees, but if I want to increase the temperature of the source, that is also possible. So, if I just now calculate T1 prime, sorry, I will use this one actually, yeah. So, T1 prime will be equal to T2, which once again is 343 divided by 1 minus eta, which is 0.5. So, basically this is 343 into 2. So, 343 into 2, which is 686 Kelvin, 686 Kelvin. So, initially the temperature is 571 Kelvin. So, delta T1 prime is equal to, or delta T1, I should not call it prime, delta T1 is equal to 686 minus 571.66 minus 571.66, which is 114.34, 114.34. So, either we have to increase the temperature, just a minute, 114.34. So, what we see is either we have to increase the temperature of the source by 114.3 Kelvin, or we have to reduce the temperature of the sink by 60 Kelvin in order to boost the efficiency point from 0.4 to 0.5, right. So, both ways this problem is solvable. Now, problem number 6, it's the following, so it's also another problem on heat engine. So, it says the following heat engines produces power of 95 milliwatt. Determine in each case the rate in milliwatt. Milliwatt means what is joules per second. So, 95 megawatt, sorry, it's capital M, so it is megawatt. So, 95 megawatt means 95 megajoules per second. Okay. Determine in case the rate at which heat is absorbed from the hot reservoir and discarded to the cold reservoir. Okay. So, both cases the work output W is 95 megawatt. Now, a Carnot engine operating between 750 Kelvin and 300 Kelvin. So, in this case we can easily calculate the efficiency. So, let us do it. So, the efficiency should be, so T1 is given as 570, T2 is given as 300 and W is 95 megajoules per second. So, the efficiency is 1 minus T2 by T1, which is equal to 0.6. Now, if the efficiency is 0.6, but by definition efficiency is W by Q1, which is equal to 0.6, W is given as 95. So, Q1 will be 95 divided by 0.6, which is 158.33 megajoules per second or megawatt, right. So, it is the same units actually. So, 158.3 megawatt should be the power or heat input to that engine in order to get a power output of 95 megawatt. Now, there is a second part to this problem. That problem says an irreversible engine operating between the same heat reservoir, but with a thermal efficiency of eta is equal to 0.35. Now, in this case we do not need the temperature of the source and the sink, because the efficiency is already given. All we have to do is we have to compute Q1. Okay. So, there are two things actually, heat is absorbed from the hot reservoir and discarded to the cold reservoir. Now, if this is the rate of heat absorbed, then Q2 is simply Q1 minus W, which is 63.33 megajoules per second. Now, in the second case, okay, so that is the first case here. Now, in the second case, when the efficiency is 0.35, we can simply use Q1 is equal to W by 0.35, which is 271.42 megajoules per second. So, Q2 will be W1 Q1 minus W, which is 176.42 megajoules per second. Of course, you see the Carnot engine has a much higher efficiency. So, it can not only it takes less amount of heat to produce same work, but also it rejects less amount of heat, whereas the other engine which has a much lower efficiency takes a large amount of heat and also rejects a large amount of heat in order to get the same amount of work. So, it is not only work efficient, boosting the efficiency of an engine not only good for power consumption, but also this amount of heat which is rejected, and most of the time this heat is directly rejected to the environment, whether to the air or to the water, which eventually ends up in the river or in the ocean. So, this leads to heat pollution, and we are every one of us, we are aware about this global warming nowadays, what is happening around us. So, this heat pollution is one of the major sources of pollution, apart from let us say air pollution and sound pollution. The temperature, of course, we know due to global warming the temperature is in general increasing, but also the engine which is less efficient produces heat in the local environment, which is not good for that part, that environment, right. Okay. So, with this we change the topic and talk about refrigerator. Now, what is a refrigerator? We are all familiar with refrigerator. Almost every one of us has a fridge in the household. This is one sort of refrigerator. If we go to a shop to buy an ice cream or a cold drinks, typically those are kept inside refrigerator. So, we are all familiar with this thing. Familiar with this with the word refrigerator. Now, what it does actually, it takes out heat from a given closed environment, whatever it is kept inside, it will take out heat from there and reject it once again in the environment. When there is a, or similarly we are all familiar with air conditioner, right. So, air conditioner, what it does, it actually takes heat from inside the room, takes out heat and rejects it outside in the environment. So, the sink which we talk about in case of an engine or in a refrigerator, for example, the sink is actually the environment, especially in case of refrigerator, right. Now, what is a refrigerator? If we go look at it schematically, it takes out heat from a cold object. Let us say it takes Q2 amount of heat, and then W amount of work has to be done on the machine, and then it will produce, it will reject Q1 amount of heat. Of course, Q1 is equal to W plus Q2. The law of conservation of energy holds as always, and so it takes lesser amount of heat from the working substance or from the substance it needs to cool, okay, or the area which it needs to cool, and then some mechanical or electrical work has to be performed on the machine. Typically, it is mechanical work at the end, but the main power source is electrical. Okay. So, in a inside, so we'll discuss it in a little elaborate manner, and then it rejects that heat into the sink. In this case, the sink temperature is more than the source temperature, right. So, this cold here is the source, hot, this is the sink, right. Now, typically what happens is, like we can define efficiency of an engine, we can define coefficient of performance of a refrigerator, which is the ratio of heat that is extracted from the cold reservoir and the work that is done on the machine, on the refrigerator. So, if it takes Q2 amount of work, Q2 amount of heat from the cold reservoir or the system of interest, and W amount of heat has to be produced on it, then my coefficient of performance W is equal to Q2 by W, sorry, omega is equal to Q2 by W, which is Q2 divided by Q1 minus Q2, right. Now, Carnot engine is a reversible engine, as in all the processes are reversible. So, if we instead of using it as an engine, if we just reverse the process, so that means it will absorb, initially it will absorb heat from the cold reservoir, and then it will then the isothermal expansion will take, isothermal compression will take place, then it will have an adiabatic compression, finally it will reject heat to the hot reservoir. So, basically if we make every process, if we invert every step in a Carnot cycle, it works as a Carnot refrigerator, which once again is a refrigerator with highest coefficient of performance. And in case of a Carnot refrigerator, reversible refrigerator, Q2 by Q1 minus Q2 can be written as T2 divided by T1 minus T2. So, I am not proving it explicitly. If you want, you can try it yourself. It is not very difficult to prove. Okay. So, all you have to do is you have to revert all the steps, when actually in a Carnot engine, heat is absorbed from Q1, heat is rejected at Q2, but in the heat is absorbed from the hot reservoir and rejected at the cold reservoir. Here it has to be opposite, heat has to be absorbed from the cold reservoir and rejected to the hot reservoir, and work has to be done on the system. Okay. So, net work has to be done on the system, then you will get back Q2 by Q1 minus Q2 is equal to T2 by T1 minus T2. And in this case or in general for a refrigerator, omega can be greater than unity. Like in case of an engine, the efficiency cannot be greater than unity. In case of omega, there is no such limitation. You see Q1 minus Q2 is always typically less than Q2, and it is in general greater than 1. Now, in a standard or household or commercial refrigerator, the work that we talk about is performed at the compressor. So, what does the compressor do? Compressor actually compresses the cooling gas, whatever the working substance, compresses the cooling gas, and then it becomes liquid under very high pressure, and we have talked about vapor liquid conversion when we were discussing Andrew's experiment on carbon dioxide. So, you can see if it is below critical point, by applying pressure you can actually make a gas into a liquid. Okay. And then what happens is there will be a place called the condenser in where it will sorry, not the condenser, it should be the evaporator, right. So, okay, I am not going to discuss it in details, but typically what happens, that gas goes through the evaporator part where that liquid goes to the evaporator part, where it becomes it gathers the energy from the chamber which has to be cooled. Okay. Then it evaporates, that is why it is called the evaporator, and then it once again goes to this compressor, and in the compressor first it goes to this condenser system where the excess heat is rejected in the environment, then it goes to the compressor where it becomes liquid again, and once again it goes into the evaporator. So, actually there are three major parts, I have not mentioned the evaporator here. So, there is a compressor, there is a there is a compressor, there is an evaporator, and there is a condenser. So, there are these three main components of a refrigerator. Okay. So, we are not going into the details of that, maybe later on when we will be discussing about real life engines, we will be revisiting refrigerator briefly. But let us go into something called the Carnot theorem. Once again, this talks about heat engine. It says working between the same two heat reservoir, no engine can be more efficient than a Carnot engine. So, this is a theorem. Once again, this cannot be it can be proved given that we accept second law of thermodynamics. We will come back to that maybe in the next class, but it was purely observational. Okay, I cannot call it observational also, because it is more of a theoretical concept to begin with, because in a as we have already discussed, a Carnot engine cannot be realized in real life. Now, if we accept this for now, we will prove it later on. Okay. So, there are two additional conclusion that comes out of Carnot theorem. These are corollary 1 and corollary 2. Corollary 1 says, working between the same two reservoir, any irreversible engine has lesser efficiency than a Carnot engine. Please remember, we keep using the word Carnot engine and a reversible engine interchangeably. Whenever an engine is reversible, we assume that this is Carnot. So, reversible engine and vice versa. So, when we say Carnot reversible engine, we mean Carnot engine and vice versa. Okay. So, please keep this in mind for the remaining discussion of remaining discussion on thermodynamics. Whenever we talk about a reversible engine, it means a Carnot engine, and the other is reverse is also true. Now, there is a second corollary, working between the same two reservoir, all Carnot engine should have equal efficiency. Okay. So, we will prove it, but till we have discussed the second law of thermodynamics. Okay. So, but this Carnot theorem has implications, like if any experiment produces an efficiency more, given that you can define the source and the sink, and if it produces an efficiency value which is more than the Carnot engine, we can blindly discard that result, because okay, once again Carnot theorem is based on second law of thermodynamics, and we so far if we accept that Carnot theorem is not valid, that means we are not accepting the second law of thermodynamics. Okay. So, without further delay, let us talk about okay. So, there are few there are few classroom problems before we go to the second law of thermodynamics. Okay. So, problem number 7 and what do we have? Problem number 7, 8 and 9, right. So, in a commercial refrigerator that operates at heat as a heat commercial refrigerator operates as a heat engine working backward in a perfectly reversible cycle between temperature 280 Kelvin and 300 Kelvin. How much heat would be removed per hour from the refrigerated space for an energy supply of 250 watts? So, basically here the source and the sink temperature is given. So, the source temperature in this case is 280 Kelvin. Please remember, for a refrigerator the source temperature is lower than the sink temperature. So, heat is taken out from this area of 280 Kelvin and it is rejected at a temperature of 300 Kelvin, which is the room temperature, and 280 Kelvin is what? 280 Kelvin is roughly 7 degrees, right. So, typically that is the temperature maintained inside a household refrigerator, 7 to 8 degrees, and inside the chill tray the temperature is inside the ice compartment the temperature is -2 degrees typically, or maybe -4 degrees, not less than that, right. Now, of course, there are modern day refrigerator which can be set at -20 degrees also, but I am just talking about the standard normal single door, the ordinary refrigerator. Okay. So, this is what we have to do is how much heat would be removed per hour. So, that we need to calculate. So, first of all, it given as a reversible refrigerator, and reversible refrigerator we have just seen that the efficiency is written as, or the coefficient of performance omega is T2 by T1 minus T2. So, T1 is 300, T2 is 280. So, we have omega is equal to 280 by 20, which is equal to 14. So, that means W2 by Q2 by W. So, omega is the heat that is absorbed from the cold reservoir or cold object and the work done on the refrigerator. Now, W is given as 250 joules per second, watts is once again 250 joules per second. Okay. So, it is 900 kilojoules per hour, right. So, we need to answer this in hour. So, how much heat would be removed per hour, right. So, 250 joules per second means we have to multiply this with 3600 to get 900 kilojoules per hour, right. So, omega is equal to Q2 is equal to omega times W, which is 14 into 900 kilojoules per hour, which is 12.6 megajoules per hour, which is 12.6 megawatt. Okay. So, if a normal refrigerator, the work is done at the compressor. So, if the compressor power is 250 watts, you can, so you can kind of approximately, and if you know the temperature outside, 300 Kelvin is the temperature of the surrounding and 250 Kelvin or 280 Kelvin is the temperature inside. What you can do is, if you take a normal lab thermometer, you can measure the temperature of your refrigerator, household refrigerator, measure the temperature of the environment, look at the compressor rating that should be written on the compressor, back of the fridge, you can look at the level, there should be some rating. If not, you can search by the model number and you can get a rating. Be careful, do not electrify yourself, be careful about it, but you can kind of calculate how much heat your refrigerator is giving away per unit time, let it be per second, let it be per hour to the environment. Okay. So, that is a very once again we are assuming that it is an ideal refrigerator. So, this equation holds, but even if you make this calculation, you will not make very big mistakes. So, typically modern day machines are kind of efficient, and especially the electric ones, they are kind of efficient, and you will get an idea. That is what I am trying to tell you. Okay. So, question number 8, in a container kept at 27 degree centigrades, ice melts at a rate of 3 kg per hour. So, when I say kept at 27 degree centigrades, I mean the outside the container, the environmental temperature is 27 degrees. If that container is now placed inside a refrigerator, what should be the minimum power of the refrigerator so the ice does not melt? Take latent heat of melting as 334 joules per gram at 0 degree centigrades. So, the question is, basically we have a refrigerator where the outside temperature is 27 degree centigrades, which is once again 300 Kelvin, and inside we have a box of ice which melts at a rate of 3 kg per hour. So, if I just keep that box as it is in the open environment, every hour 3 kg of ice will melt, right. Now, we have to maintain that box at 0 degree centigrade, so that the ice does not melt. So, of course, if we maintain it at -2, it will be even better, but as it is required to compute the minimum amount of heat, minimum power, we will consider that temperature of the source, in this case the low temperature part, is 0 degree centigrades. So, we have T1 is equal to 300 Kelvin, T2 is equal to 273 Kelvin. So, from the surrounding, heat enters the container at a rate of 3 into 10 to the power 3 into, so this is latent heat is given. So, that means the total heat that enters, because the ice melts at a rate of 3 kgs per hour. So, that means 3 into 10 to the power 3 grams per hour. So, the total heat is 3 into 10 to the power 3 into 334 joules per hour, which is 100.2 into 10 to the power 4 joules per hour. Now, that amount of heat has to be taken away from that container, so that the temperature is maintained at 0 degree centigrades, right. So, for a reversible refrigerator, so for the and once again we are computing the minimum power. Minimum power is obtained when we are using a reversible refrigerator with the coefficient of performance W is equal to T2 by T1 minus T2, which is 273 by 27, which is so I have not calculated 270, it remains as 273 by 27. So, this is Q by W. So, the Q is given, Q is 100.2 into 10 to the power 4 joules per hour. So, this amount of heat has to be removed, right. So, actually I should write Q2 here, then it will be easy for you, right. Q2 by W, right. Now, what we have to do is we have to compute W, which is Q2 into 27 divided by 273. So, if I put that, this is my number, this is my work done per hour. Now, what do we need? We need to compute per, so we want to give it in a more convenient units. So, what we do is we just divide it by 3600 and convert it to joules per second instead of joules per hour, and we get 27.5 watt, right. So, something is not right here. I think it should be 275 watts. Okay, I just need to check this once again, because the previous problem we got 250 watts and this is 27.5. Okay, I think I have missed a factor of 10. Okay, let us do it. So, 27 into 100.2 into 10 to the power 4 divided by 273, right, divided by 3600, right. No, 27.5. Anyway, I will look into this calculation, maybe I made a mistake somewhere, maybe in this number itself there is a mistake, but I will look into it, right. But I think you got the idea. So, how to solve this problem? If there is a mistake, I will correct it in the final class note version, otherwise it stays as it is. So, you got the idea. So, all we have to do is we need to first compute the amount of heat that is being taken out by this relation. Then we compute the efficiency given that the refrigerator is completely reversible, and from there we compute the amount of work done W by this simple relation, and finally we convert it into power, right. So, we come to the last problem of this lecture. We have a company claims that their engine delivers an output of 1 kilowatt and absorbs energy at a rate of 65 kilojoules per minute from a source at 1127 degree centigrades and discard the heat in the surrounding at 27 degree centigrades. Is the claim justified? So, this is the question. So, basically what is given is work output, the heat input is given here, source temperature and the sink temperature is given here. So, what all we need to do is we need to compute the efficiency. T1, T2 is given. The maximum possible efficiency, that is for a Carnot engine, is eta C is equal to 0.7857. So, this is the maximum efficiency. The efficiency claimed by the company is for their engine, which we call eta E, is equal to W by Q1, which is 10 to the power 3 joules per second divided by 65 into 10 to the power 3 joules per second divided by 60, because it is given as 65 kilojoules per minute. So, we just have to divide it by 60 once again, and we get an efficiency of 0.9231. So, the engine efficiency claimed by the company is more than the efficiency of a Carnot engine operating between the same two heat reservoirs. Now, according to Carnot theorem, that is not possible. So, the claim is false, right. Now, with this we come to the last part of our discussion today, which is second law of thermodynamics. Now, once again the second law, as just like the first law, it cannot be proved. It comes out as a series of observation and theoretical discussion, theoretical brainstorming. It cannot be proved, but if we accept second law, we get so many results that we can, in case if we accept second law of thermodynamics, we can explain so many experimental observation in a correct manner that So far there has been no doubt about the second law of thermodynamics. So, same goes for the first law. These laws cannot be proved, we need to accept it, but it can, if we accept those, all the experimental results can be justified by the logic of those laws. So, there are two statements available for the second law of thermodynamics, and in the next class we will show you that these two statements are actually equivalent. So, for today's lecture we will simply state these two statements and call it a day. So, the Clausius statement, which was given in 1850, says no process is possible whose sole result is the transfer of heat from a colder to a hotter body. What I mean by this is, in Clausius statement it actually discards the concept of an ideal engine. An ideal engine, ideal refrigerator. Ideal refrigerator needs no work. It takes, so going back here, an ideal refrigerator the amount of coefficient of performance is infinity. So, it does not need any W, okay. It just takes Q2 amount of heat and discards the same Q2 amount of heat to the hot reservoir without any external work, right. So, it is kind of a perpetual machine, right. So, the Clausius statement discards the possibility of a ideal refrigerator, and then Kelvin-Planck statement, actually the Kelvin and Planck separately made two statements which were later combined into one single statement that says no process is possible whose sole result is to absorption of heat from a reservoir and convert it completely to work. So, the Kelvin-Planck statement actually discards the concept of an ideal heat engine. So, that means, if in an ideal heat engine the work output the heat output to the sink is equal to 0 and the efficiency 1 minus Q2 by Q1, right, and if Q2 is equal to 0 then the efficiency becomes 1. So, Kelvin-Planck statement, not only the third law of thermodynamics, but also Kelvin-Planck statement discards the concept of an ideal heat engine. So, Clausius statement discards the concept of an ideal refrigerator and Kelvin-Planck statement discards the concept of ideal heat engine. Now, if you look into any standard textbook, you might find these statements in a much flowery language. Basically the same thing. What I did here, I just abridged those statements in a very simple language, tried to put it in a simple language without altering its essential message and put it here. Anyway, so in the next class what we are going to do is, we are going to talk about the equivalence of this Kelvin-Planck and Clausius statement, and then if we accept these laws, which are the two statements of second law of thermodynamics, we will see that we can actually prove Carnot theorem given that these laws are valid. Okay. So, then Carnot theorem will be proved and we will take it one step forward into something called the Clausius inequality, and from there we are going to discuss or going to define a quantity called the entropy of a system. Okay. So, till then, goodbye.